the true scale of a single solar flare will terrify you. Tonight, we're going to look at the single most powerful explosion that it has already happened many times while you were alive, and you almost certainly never noticed. It begins as a flash, a sudden, brilliant flare of light erupting from the surface of the sun, 93 million miles away. From here, it looks like nothing at all, just a bright spot on a star we cannot even safely look at. But that flash is not nothing. That flash is the most violent event our corner of the universe ever produces. In a matter of minutes, space used in thousands of years. It can unleash the power of billions of nuclear weapons, all at once, in one blinding eruption. It can heat matter to temperatures hotter than the very core of the sun, and it can span an area so vast that you could line up dozens of Earths across it and still not reach the other side. This is not a small thing happening far away. This is the largest explosion in the solar system, and it happens regularly, right above our heads. And here is what should genuinely give you pause. These flares are not largest, terrifyingly close to crippling modern civilization. One has already knocked out the power for millions of people in a matter of seconds. Another, just over a decade ago, was powerful enough to send us back to the 19th century, and it missed the Earth by a margin of just 9 days. We live, every single day, beneath a star capable of producing an explosion so large it could collapse our power grids, destroy our satellites, and silence our communications across entire continents. And most people have no idea. By the end of tonight, you're going to understand the true scale of a single solar flare, how much energy it really contains, how it is created, just how big and how hot it is, and why the largest ones represent one of the most underestimated threats our technological civilization faces. This is the story of the most powerful explosion in the solar system, and why you should be paying attention to it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why a solar flare is so terrifying, you first have to understand how easy it is to miss one. Because the most powerful explosions in the solar system happen in near total silence, as far as we are concerned, and the gap between how harmless they appear and how monstrous they actually are is the whole reason they are so dangerous. When a solar flare erupts, there is no sound that reaches us, no shaking of the ground, no warning siren. From the surface of the Earth, even a major flare is completely invisible to the naked eye, lost in the overwhelming brightness of the sun. You could be standing outside, going about your day. At the exact moment the sun unleashes an explosion equivalent to billions of nuclear bombs, and you would feel nothing, see nothing, know nothing. The flash happens, the energy pours out across space, and life on Earth continues, seemingly undisturbed. This is the strange our solar system, and from our vantage point, almost completely imperceptible. We are shielded from their full fury, most of the time by distance and by the invisible defenses of our planet. And because of this, it is incredibly easy to underestimate them. We do not have a visceral, gut-level fear of solar flares the way we fear earthquakes, or hurricanes, or wildfires, because we have never directly felt one. They do not register in our daily experience. They happen far away, silently, and for the most part harmlessly. So we ignore them. We go about our lives, rarely sparing a thought for the colossal explosion. single day. The sun could be in a state of violent eruption right now, this very moment, and you would have no way of knowing just by looking up. But this comfortable ignorance hides a genuine danger, because while most solar flares pass us by without consequence, the largest ones do not. The largest ones have the power to reach across that vast gulf of space and touch our world in ways that could be catastrophic for a civilization as dependent on technology as ours has become. The flash you would never notice is, in reality, a glimpse of a force so immense that it humbles everything humanity has ever built. And to truly grasp that force, to feel the genuine scale of it, we have to start by understanding exactly what a solar flare is, and what is actually happening in that brilliant, silent flash on the face of the sun. So what exactly is a solar flare? We throw the term around, and we have a vague sense of it as some kind of solar outburst. But the reality is both more specific and more astonishing than most people realize. A solar flare is, quite simply, the most powerful explosive event that occurs anywhere in our entire solar system. Nothing else our sun does, nothing that happens on any of the planets, comes close to the raw power unleashed in a major solar flare. At its heart, a solar flare is a sudden, intense burst of radiation, an enormous release of energy from the surface of the sun. When a flare erupts, a region of the sun's surface suddenly brightens dramatically, blazing with a flash of light and radiation across many different wavelengths, from visible light to ultraviolet to powerful X-rays and beyond. This is not a gradual brightening. It is an explosion, a sudden and violent release of energy that had been building up and storing itself in the sun's atmosphere. In the space of minutes, a region of the sun unleashes a torrent of energy so vast that it momentarily outshines the area around it, pouring radiation out into space in all directions. Some of that radiation, inevitably, comes streaming toward Earth. It is important to understand that a flare is fundamentally a release of energy that was already stored, waiting on the sun. The sun's atmosphere, its outer layers, can build up enormous amounts of energy in its powerful and complex magnetic fields, like a spring being wound tighter and tighter, or a dam holding back an ever-growing reservoir. A solar flare is the moment that stored energy is suddenly and explosively released, all at once, converting into the brilliant flash of radiation we observe. It is the sun violently discharging energy that had accumulated in its magnetic fields, in an eruption so powerful it defies easy comparison to anything in our experience. We will come to exactly how that energy gets stored and released, because the mechanism is genuinely remarkable. But first, you need to grasp the sheer quantity of energy involved. And here is a crucial detail that makes flares so relevant to us. Because a flare releases its energy largely as radiation, as light and X-rays and other forms of electromagnetic energy, that energy travels at the fastest speed in the universe, the speed of light. This means that when a flare erupts on the sun, the radiation it produces reaches the Earth in about 8 minutes, the same time it takes ordinary sunlight to cross the gulf between the sun and our planet. There is essentially no warning. By the time we detect the flash of a major flare, its radiation is already arriving. The most powerful explosion in the solar system announces itself and strikes almost simultaneously, crossing 93 million miles in the time it takes to brew a cup of coffee. But the true horror and the true wonder of a solar flare only becomes clear when you understand just how much energy that 8-minute journey is carrying. And that number is almost impossible for the human mind to hold. Let's confront, directly, the single most staggering fact about a solar flare: the amount of energy it releases. Because this is the number that transforms a flare from an interesting astronomical curiosity into something genuinely awe-inspiring and, frankly, terrifying. And it is a number so large that, like so much about space, your mind will struggle to truly grasp it. A single large solar flare can release an amount of energy equivalent to billions of nuclear bombs detonating all at once. Let that begin to sink in. Not one nuclear bomb, not 100, not 1,000, billions of them. The energy unleashed in a major solar flare, when scientists calculate it and compare it to weapons we understand, comes out to the equivalent of billions of the nuclear bombs of the kind that devastated entire cities. All of that energy, released in a span of minutes, in a single eruption on the surface of the sun. It is a quantity of energy so far beyond anything in human experience that we have no real frame of reference for it. The most powerful weapons our species has ever built are, individually, utterly insignificant next to a single solar flare. And we can push the comparison even further, because nuclear bombs come in many sizes, and the largest ever built dwarf the ones used in war. Even measured against the most powerful hydrogen bombs humanity has ever detonated, weapons thousands of times more powerful than early atomic bombs, a single great solar flare can release energy equivalent to over 1 million of them. Picture that. Take an ever created by human hands, a hydrogen bomb capable of flattening a vast area, and then imagine over 1 million of them going off simultaneously. That is the your solar flare. It is not an exaggeration or a metaphor. It is the actual, calculated energy output of these eruptions, expressed in terms of the most powerful explosions we know how to create. And our most powerful explosions still fall millions of times short. There is another way to feel the magnitude of this, and it may be the most humbling of all. The energy released by one of the largest solar flares ever recorded is comparable to the total amount of energy the sun radiates from its entire surface in several seconds. Think about what that means. The sun is pouring out energy across its whole vast surface, enough to light and warm the entire solar system, and a single flare can concentrate, in one localized eruption, a meaningful fraction of that staggering total output. The flare takes the kind of power that the entire sun radiates in seconds and unleashes it in a single, focused explosion. This is why a solar flare is the most powerful explosive event in the solar system. It is, in a real sense, the sun briefly concentrating its unimaginable power into a single, violent flash. And to truly appreciate what billions of nuclear bombs worth of energy means, we need to translate it out of the language of weapons and into terms that connect to our own lives. Numbers like billions of nuclear bombs are so large that they almost lose their meaning. The mind simply cannot picture billions of explosions. So let's try to translate the energy of a solar flare into terms that connect more directly to human experience. Because doing so reveals just how absurdly, almost incomprehensibly powerful these eruptions are compared to everything our species does. Consider all the energy used by the whole of human civilization. Every power plant, every car, every factory, every home, every device, across the entire planet, all the electricity and fuel and power consumed by all 8 billion people on Earth. Now consider how much energy that adds up to over a year. It is an enormous amount, the total energy appetite of our entire global civilization. And yet, a single large solar flare can release, in just a few minutes, far more energy than all of humanity consumes in not just 1 year, but in thousands of years. Picture that. Everything human beings do, all our collective energy use, scaled up across thousands of years of civilization, and a single flash on the sun, lasting only minutes, can exceed it. The disparity is almost impossible to comprehend. In the time it takes a flare to erupt and fade, the sun has released more energy than our entire species would use across vast stretches of history. This comparison reveals something profound about our place in the cosmos. We tend to think of human civilization as powerful. We have harnessed enormous amounts of energy. We light up entire cities, power global industry, launch rockets into space. By our own standards, we command tremendous power. And yet, the sun, in a single one of its countless flares, casually outproduces the entire energy output of our civilization across millennia. And it does this routinely, sometimes multiple times in a single day, without any effort, without any consequence to itself. The power we are so proud of is a flicker next to a single solar flare. It is a sobering reminder of just how small our mightiest achievements are against the backdrop of what the universe does as a matter of course. And remember, this colossal energy is not released slowly. Over the thousands of years it would take humanity to use the equivalent. It is released almost instantaneously, in the span of minutes. It is the concentration of the energy that matters as much as the quantity. Imagine taking thousands of years of all human energy use and compressing it into a few minutes, releasing it all in one violent burst. That sudden, concentrated release is what makes a flare an explosion rather than a gentle outpouring. The energy does not trickle out, it detonates. And this is happening on the surface of the very star that gives us life, the same sun that rises gently each morning and warms our faces. That benign, familiar sun is capable of explosions that dwarf everything humanity has ever done, compressed into mere minutes. But the energy is only one dimension of a flare scale, because these explosions are not just unimaginably powerful, they are also unimaginably large. We have talked about the energy of a solar flare, but energy is only one part of its scale. There is also its sheer physical size, the actual extent of the eruption across the surface of the sun. And here, too, the numbers shatter our human intuition, because a single solar flare can be so large that our entire planet would be lost inside it like a pebble in a wildfire. To understand the size of a flare, you first have to remember the size of the sun itself, which is already almost beyond comprehension. The sun is enormous, so vast that you could fit over 1,000,000 Earths inside it. Its surface is a churning, seething ocean of superheated plasma, stretching across a face so large that our entire world would be a tiny speck against it. And a solar flare does not erupt from the whole sun. It erupts from a region of the surface, an active area where the magnetic fields are concentrated. But even that single region, that one patch of the sun where a flare ignites, can be staggeringly large. The active regions that produce major flares can span areas many times the size of the entire Earth. A single such region can be tens of thousands of miles across, large enough that you could line up many Earths side by side across it. Picture that for a moment. The flash of a solar flare can erupt across an area of the sun's surface so large that you could fit dozens of Earths within it. If you could somehow place our planet next to the region where a major flare erupts, the Earth would be dwarfed, a small marble against a vast, blazing expanse. The eruption is not a small, localized spark on the sun. It is an explosion spanning a region larger than many planets put together, a flash of energy erupting across a swath of the sun bigger than anything in our planetary experience. The scale is simply not something our minds are built to handle. We are used to explosions measured in feet or miles. A solar flare is measured in multiples of entire worlds, and the flare is not confined to the flat surface. The eruption reaches upward, outward, into the sun's atmosphere, often along great arcing loops of magnetic field that tower above the surface. These coronal loops, the glowing arcs of plasma that trace out the magnetic fields involved in a flare, can rise to heights many times the diameter of the Earth, soaring tens of thousands of miles or more above the solar surface. So a flare is not just enormously wide. It is enormously tall as well, a three-dimensional eruption of colossal proportions, with arcs of glowing plasma towering over a region larger than multiple planets. If you could stand back and watch a major flare erupt at its true scale, with the Earth placed beside it for comparison, the sight would be almost incomprehensible. Our entire world, every continent and ocean, every living thing, would be a minor detail at the edge of an explosion vast enough to swallow it many times over. But the size of a flare, staggering as it is matched by another extreme that is just as hard to fathom. Its temperature. We have seen that a solar flare is unimaginably energetic and unimaginably large. Now let's add the third dimension of its scale, one that is perhaps the most surprising of all: its temperature. Because when a solar flare erupts, it heats the material involved to temperatures so extreme that, for a brief moment, parts of the flare can become hotter than the very core of the sun itself. And the core of the sun, remember, is the hottest place in the entire solar system under normal conditions. Let's establish the baseline first. The surface of the sun, the part we see, is already astonishingly hot, around 10,000 degrees, hot enough to vaporize any material we know of instantly. Go deeper down to the core of the sun, where nuclear fusion takes place, and the temperature soars to around 15 million degrees. That core temperature is almost beyond comprehension, the searing heart of our star, hotter than anything else in the solar system. It is the standard against which all other temperatures in our cosmic neighborhood are measured. Nothing, under normal circumstances, is hotter than the core of the sun. And yet, a solar flare can challenge even that. When a flare erupts, the sudden, violent release of energy heats the plasma in the flare to extraordinary temperatures, reaching tens of millions of degrees. In the most intense flares, the temperatures in certain regions can climb to levels that rival, and even briefly exceed, the temperature at the core of the sun. Think about how staggering that is. The core of the sun is heated by the relentless, continuous process of nuclear fusion, the most powerful sustained energy source in the solar system. And yet, a solar flare, through the sudden release of stored magnetic energy, can momentarily heat its plasma to temperatures hotter than that core. The flash of a flare is, for a brief instant, one of the hottest places anywhere in the solar system, a pocket of matter superheated beyond even the furnace at the heart of our star. The explosion is so violent that it briefly out-heats the core of the sun, right there on the surface. This extreme heat is part of what makes a flare radiate so intensely, and why it pours out such powerful, high-energy radiation. The superheated plasma in the flare blazes with energy, emitting not just visible light but enormous quantities of ultraviolet light and X-rays, the kind of high-energy radiation produced only by matter at extreme temperatures. This is why flares are detected and measured largely by their X-ray output, because the searing temperatures of the flare generate floods of X-rays that stream across space. So a solar flare is not only a release of energy equivalent to billions of nuclear bombs, and not only an eruption spanning an area larger than many Earths. It is also a flash of matter heated hotter than the core of the sun, blazing with radiation across the spectrum. Every dimension of its scale, energy, size, and temperature pushes far beyond anything in human experience. But all of this raises an obvious and fascinating question. Where does all this energy come from? How does the sun store up the power of billions of nuclear bombs and then release it in a single violent flash? The answer lies in the invisible architecture of the sun's magnetic field. We have established the terrifying scale of a solar flare, its energy, its size, its heat. But we have not yet answered the most fundamental question. What actually causes it? What is the engine that stores up the energy of billions of nuclear bombs and then unleashes it all at once? The answer is one of the most elegant and powerful processes in all of nature, and it involves something invisible, yet immensely powerful: the sun's magnetic field. The sun is not just a ball of hot gas. It is a churning, electrically charged object, and as that charged material moves and flows, it generates powerful magnetic fields. These magnetic fields thread through the sun and arc out above its surface, forming an intricate, ever-changing architecture of magnetic loops and lines. Now here is the crucial point. Magnetic fields can store energy, much like a stretched rubber band or a coiled spring stores energy. And the magnetic fields of the sun, especially in the active regions where flares are born, become enormously stressed and contorted. The constant churning of the plasma at the sun's surface drags and twists the magnetic field lines, winding them up, tangling them, stretching them into increasingly complex and strained configurations. As this happens, more and more energy gets stored in the twisted, stressed magnetic field, like a spring being wound tighter and tighter, or a rope being twisted until it is straining to unwind. This stored magnetic energy can build up to colossal levels. The magnetic fields in an active region can become wound up like a vast, invisible reservoir of energy, holding within their twisted structure the equivalent of billions of nuclear bombs, all coiled and waiting. But a wound-up spring cannot stay wound forever. At some point, the strain becomes too great, and the system suddenly snaps to a simpler, more relaxed configuration, releasing all that stored energy at once. In the sun, this snapping happens through a process called magnetic reconnection. When the stressed, twisted magnetic field lines are pushed to their limit, they suddenly break and reconnect into a new, simpler arrangement. And in doing so, they violently release the enormous energy that had been stored in their twisted structure. That sudden release of magnetic energy is the solar flare. Magnetic reconnection is, in essence, the trigger and the engine of the solar flare. It is the moment the wound-up spring lets go, the moment the straining magnetic fields snap to a lower energy state and dump all their stored energy into the surrounding plasma. That released energy heats the plasma to the tens of millions of degrees we discussed, accelerates particles to enormous speeds, and produces the brilliant flash of radiation that is the flare. All of the flare's terrifying power, its energy, its heat, its radiation, comes from this sudden release of magnetic energy that had been slowly, patiently building up in the twisted fields of the sun's active regions. The sun spends days or weeks winding up its magnetic fields, storing energy, and then, in a matter of minutes, releases it all in a single, violent snap. It is a process of slow accumulation and sudden, explosive release, and it is happening constantly on the surface of our star. To really appreciate it, we need to look more closely at how these magnetic traps are built in the first place, in the dark, churning regions we call sunspots. To understand where a solar flare's colossal energy comes from, we have to look at the places on the sun where these eruptions are born. And those places are marked by some of the most recognizable features on our star: dark blotches on the bright surface of the sun, known as sunspots. These sunspots are the visible signatures of the intense, twisted magnetic fields that store the energy for a flare, and understanding them is key to understanding the entire process. Sunspots are regions on the sun's surface that appear darker than their surroundings. For centuries, observers have noticed these dark patches coming and going on the face of the sun. But what are they really? A sunspot is a region where the sun's magnetic field is extraordinarily strong and concentrated, so strong that it actually punches up through the surface and arcs out into the sun's atmosphere. And here is the fascinating part. This intense magnetic field is what makes the spot appear dark. The powerful magnetic field in a sunspot suppresses the normal churning motion of the hot plasma that would otherwise carry heat up to the surface. With that flow of heat partly blocked, the region cools slightly, becoming somewhat cooler than the surrounding surface. And because it is cooler, it glows a little less brightly, appearing dark by contrast against the brilliant surface around it. So a sunspot is not actually a hole or a cold spot in any ordinary sense. It is a place where a knot of intense magnetism has broken through the surface, cooling it just enough to look dark. These sunspots are where the magnetic fields are most concentrated and most stressed, and therefore they are the launch pads for solar flares. The twisted, tangled magnetic fields that emerge through sunspots are exactly the wound-up springs we talked about, the reservoirs of stored magnetic energy. As the plasma beneath the surface churns and rotates, it drags these magnetic fields around, twisting and contorting them, winding them ever tighter. In a large, complex group of sunspots, the magnetic fields can become incredibly tangled and strained, storing up enormous amounts of energy in their contorted structure. The more twisted and complex the magnetic field becomes, the more energy it stores, and the more primed it becomes for a violent release. This is why the largest flares tend to come from the largest, most magnetically complex sunspot groups, where the most energy has been wound up and stored. And these sunspot groups can be staggeringly large in their own right. A major group of sunspots, the kind that produces powerful flares, can stretch across an area many times the size of the Earth. Picture a region on the sun, dark with intense magnetism, large enough to swallow our entire planet several times over, with magnetic fields twisting and straining beneath it, storing the energy of billions of nuclear bombs. That is the setting where a solar flare is born. The number of these sunspots, and their size and complexity, rises and falls over the sun's 11-year cycle of activity. During the most active periods, the sun can be peppered with large, complex sunspot groups, each one a potential source of a major flare. And when one of these magnetic reservoirs finally reaches its breaking point, the result is the violent snap of magnetic reconnection and the explosion of a solar flare. To truly feel the violence of that moment, let's slow it down and look at exactly what happens in the instant a flare erupts. We have built up to the moment of eruption. The magnetic fields have been twisted and wound for days, storing colossal energy, straining toward their breaking point. And then, in an instant, they snap. Let's slow down that moment and look closely at what actually happens when a solar flare erupts, because the violence and speed of it are genuinely astonishing, and it all unfolds in a matter of minutes. When the stressed magnetic fields finally reach their limit, magnetic reconnection occurs. The twisted field lines suddenly break and rearrange themselves into a simpler, less strained configuration, and in that instant, the vast energy that had been stored in their twisted structure is violently released. This release is not gentle, it is explosive. All at once, the stored magnetic energy converts into other forms, heating the surrounding plasma, accelerating particles, and producing radiation. The plasma in the flare region is suddenly superheated to tens of millions of degrees, blazing with energy. And charged particles, the electrons and ions in the plasma, are caught up in the reconnection and flung outward at tremendous speeds, accelerated to a significant fraction of the speed of light. In a single moment, the quiet, wound-up magnetic field becomes a violent storm of superheated plasma and high-speed particles. The radiation pours out instantly across the entire spectrum. The flare blazes with visible light, but also with enormous quantities of ultraviolet light and powerful X-rays, and even more energetic radiation, all produced by the superheated plasma and the accelerated particles. This flood of radiation is the flash we detect as the solar flare, the brilliant burst of energy erupting from the sun's surface. And the particles that are accelerated by the reconnection go racing off in different directions. Some are flung downward, slamming into the denser layers of the sun below, causing regions at the base of the magnetic loops to blaze brightly. Others are hurled upward and outward, escaping the sun entirely and racing off into space as streams of high-energy particles, particles that can themselves pose a hazard, as we will see. What makes this so remarkable is the speed and scale of it all. Days or weeks of patient energy storage are undone in minutes. The colossal reservoir of magnetic energy, equivalent to billions of nuclear bombs, is released in a single, violent eruption that builds to its peak and then fades, all within a relatively short span of time. It is one of the most sudden and powerful transformations in all of nature, the near instantaneous conversion of stored magnetic energy into heat, light, radiation, and high-speed particles, on a scale that dwarfs anything humanity can produce. The snap of a solar flare is the universe demonstrating, right on the surface of our own star, just how much power can be stored in a magnetic field, and how violently it can be released. And scientists, watching this happen again and again, have developed a way to measure and categorize these eruptions, a scale that reveals just how enormous the range of flare power really is. Solar flares are not all the same. They range from minor eruptions that have almost no effect on Earth to monstrous explosions capable of disrupting our entire technological civilization. To make sense of this enormous range, scientists have developed a classification system for solar flares, a scale that sorts them by their power. And understanding this scale reveals just how vast the difference is between an ordinary flare and a truly dangerous one. Solar flares are classified based on the intensity of the X-rays they produce, since the X-ray output is a good measure of a flare's overall power. The classification uses letters to denote different levels of intensity. The weakest flares are given the earliest letters, and as flares grow more powerful, they move up through the letter classes. The main classes, from weaker to stronger, run through a sequence culminating in the most powerful category, the X-class flares. An X-class flare is the most intense type, the heavyweight of solar eruptions. But here is the crucial detail that reveals the true scale. This classification is logarithmic. That means each step up the scale represents not a small increase, but a tenfold increase in power. A flare one class higher than another is 10 times more powerful. So the difference between the classes is not gradual. It is exponential, with each class packing 10 times the punch of the one below it. Let that sink in, because it transforms how you understand the range of flares. A flare in the most powerful X-class is not just a little stronger than the classes below it. It is vastly, exponentially more powerful, 10 times stronger than the class below it, 100 times stronger than the class below that, and so on. The jump from a moderate flare to a major X-class flare is a jump across orders of magnitude in energy, and even within the X-class itself, there is a huge range. X-class flares are numbered to indicate their strength, and these numbers can climb high. An X-class flare with a higher number is proportionally more powerful, so an X-class flare numbered in the 20s or beyond is many times more powerful than one numbered at the low end of the class. The most powerful flares sit at the very top of this scale, representing the absolute extremes of what the sun can produce. This classification system is not just an academic exercise. It directly relates to the danger a flare poses to Earth. The weaker classes of flares are common and generally harmless, occurring frequently with little effect on our planet. But as you climb into the more powerful classes, especially the X-class flares, the potential for disruption grows dramatically. The stronger flares, particularly those rated in the upper classes, can begin to affect the technology we depend on, interfering with radio communications, navigation systems, and more. And the most extreme flares, the rare monsters at the very top of the scale, carry the potential for genuine catastrophe. So when scientists announce that the sun has produced a powerful X-class flare, they are telling us that one of the most energetic events in the solar system has just occurred, and that, depending on its strength and direction, it could have real consequences for our world. To appreciate just how extreme these eruptions can get, let's look at the most powerful flares ever recorded, and at a recent period when the sun has been unusually, alarmingly active. We have established that solar flares range across an enormous scale, with the most powerful X-class flares representing the extreme upper end. So just how powerful can a flare get? What are the largest eruptions ever recorded? The answer pushes the limits of even our measuring instruments, and reveals that the sun is capable of explosions so intense that, on at least one occasion, it overwhelmed the very detectors built to measure it. The most powerful solar flare ever recorded erupted just over 2 decades ago, during a period of intense solar activity. This flare was so enormous that it actually saturated the X-ray detectors that scientists use to measure flare intensity. The instruments simply maxed out, unable to register the full force of the eruption, and scientists had to estimate the flare's true strength from the available data. The best estimates placed it far beyond the threshold of the X-class, at a level many times more powerful than a flare at the bottom of that already extreme category. It was a monster, an eruption so violent that it exceeded the range of our instruments, the single most powerful solar explosion humanity has ever directly measured. This flare was part of a series of intense eruptions during that period, a stretch of solar fury that produced some of the most powerful flares ever seen, reminding us of just how extreme the sun can become. And lest you think such extreme activity is safely confined to the past, consider what the sun has been doing very recently. In the last couple of years, the sun has entered the most active phase of its 11-year cycle, the period known as solar maximum, when flares and eruptions become far more frequent. And this recent solar maximum has been surprisingly, even alarmingly, active. In a single recent year, the sun produced a record number of powerful X-class flares, more than in any year in the decades since detailed records began. The sun has been erupting with major flares again and again, a relentless barrage of powerful explosions, far more than scientists had initially predicted for this cycle. The most powerful flare of this recent period was a major X-class eruption, a reminder that the sun is fully capable of producing dangerous flares right now, in our own time. This recent surge of activity is a crucial point, because it dispels any sense that powerful solar flares are a rare, historical concern. They are not. The sun is producing major flares regularly, right now, and the current period of heightened activity may continue for some time. Every one of these powerful flares is an eruption equivalent to billions of nuclear bombs, occurring on the surface of our star, sometimes multiple times in a short span. Most of them, fortunately, are either not aimed at Earth or not quite powerful enough to cause major harm. But each one is a roll of the dice, and the more powerful flares the sun produces, the greater the chance that one of them will be both large enough and aimed directly enough at us to cause real trouble. The sun has been remarkably active, and that activity is a live, ongoing reality, not a distant memory. And when a flare does erupt toward Earth, the first thing to reach us travels at the fastest speed in the universe, arriving with virtually no warning at all. When a solar flare erupts on the sun and its radiation comes streaming toward Earth, how much warning do we get? The answer is genuinely unsettling. Almost none. Because the radiation from a solar flare travels at the speed of light, the fastest anything can possibly move in the universe, and that means it crosses the vast gulf between the sun and the Earth in only about 8 minutes. The most powerful explosion in the solar system gives us virtually no time to prepare. Think about what this means. A solar flare erupts. In that instant, a flash of intense radiation, including powerful X-rays and ultraviolet light, begins racing toward Earth at the speed of light. And just 8 minutes later, that radiation arrives at our planet. There is no meaningful warning period. By the time the light from the flare reaches us, allowing us to even detect that the flare has occurred, its radiation is arriving simultaneously. We see the flare and feel its effects at essentially the same moment, because the light that lets us see it and the radiation that affects us are traveling together at the same speed. We cannot detect a flare before its radiation arrives, because nothing travels faster than that radiation. The flash and the impact are, for all practical purposes, simultaneous. This is fundamentally different from many other natural hazards where we get at least some warning. With a solar flare's radiation, the warning and the event arrive together. And this initial burst of radiation, arriving in 8 minutes, has immediate effects on the side of the Earth facing the sun. The powerful X-rays and ultraviolet radiation from a major flare slam into the upper layers of Earth's atmosphere, the region known as the ionosphere, and disturb it. This can cause immediate disruptions to radio communications, particularly the high-frequency radio signals that bounce off the ionosphere to travel long distances. During a major flare, these radio signals can be degraded or blacked out entirely across the sunlit side of the Earth, sometimes for minutes or hours. Aircraft on long routes, ships at sea, and others who rely on high-frequency radio can suddenly find their communications disrupted, all because of an explosion on the sun that occurred just 8 minutes earlier. This is the first wave of a flare's impact, the radiation that arrives almost instantly and immediately affects our technology. But here is the critical thing to understand. This 8-minute radiation is only the first part of the story, and often not the most dangerous part. Because while the radiation arrives in 8 minutes and causes these immediate effects, a major solar eruption often launches something else as well, something slower but potentially far more destructive. The radiation is the flash, the immediate burst of light and X-rays. But following behind it, traveling much more slowly, can come a vast cloud of actual matter, billions of tons of charged particles blasted out from the sun. This is the part of a solar eruption that can cause the truly catastrophic effects on Earth, and it is to this terrifying cloud that we now turn. Because if the flare itself is the flash, the cloud behind it is the cannonball. The radiation from a solar flare is only the beginning. The truly dangerous part of a major solar eruption is often something that comes behind the flash, something made not of light, but of matter. When the sun erupts, It can hurl out into space an enormous cloud of charged particles, a vast bubble of solar material blasted away from the surface. This is called a coronal mass ejection, and it is in many ways the part of a solar storm we should fear most. A coronal mass ejection, often shortened to a CME, is a colossal eruption of plasma and magnetic field from the Sun's outer atmosphere. When one of these occurs, the Sun flings out into space an almost unimaginable quantity of material, billions of tons of charged particles, electrically charged gas torn from the Sun and launched outward. Picture that. Billions of tons of matter, blasted off the surface of the Sun and sent hurtling through space. This is not radiation. This is actual physical substance, a massive cloud of charged particles racing outward, carrying with it the Sun's tangled magnetic field. And these clouds are launched at tremendous speeds, racing away from the Sun at up to millions of miles per hour. A coronal mass ejection is like a cannonball of solar material, fired out from the Sun, sometimes directly toward Earth. Unlike the radiation from a flare, which reaches us in 8 minutes, a coronal mass ejection travels much more slowly because it is made of matter rather than light. Even moving at millions of miles per hour, it still takes time to cross the vast distance to Earth, typically arriving 1 to 3 days after it is launched, though the very fastest ones can arrive considerably sooner. So when a major eruption occurs on the Sun, we may get a flash of radiation in 8 minutes, and then, a day or so later, the arrival of the cloud of charged particles itself. This delay actually gives us some warning for the CME, unlike the radiation. When scientists observe a major eruption launching a CME toward Earth, they can estimate when the cloud will arrive and warn that a geomagnetic storm may be coming. But knowing it is coming does not necessarily mean we can prevent the damage it may cause. Because when a coronal mass ejection reaches Earth, it can slam into our planet's magnetic field and cause a geomagnetic storm, a major disturbance of the Earth's magnetic environment. And it is these geomagnetic storms, triggered by the arrival of the CME, that can cause the most severe and destructive effects on our technology. The cloud of charged particles, with its embedded magnetic field, interacts violently with the Earth's magnetic field, inducing electrical currents, disrupting satellites, and potentially wreaking havoc on the systems we depend on. The flash of the flare is dramatic, but it is the slower, heavier cloud behind it, the coronal mass ejection, that carries the real destructive potential. And the only reason this billion-ton cannonball of solar material does not simply destroy life on Earth outright is that our planet possesses a remarkable, invisible defense, a shield that has protected life for billions of years. If the Sun regularly hurls out radiation equivalent to billions of nuclear bombs and launches billion-ton clouds of charged particles at our planet, then why are we still here? Why has life on Earth not been sterilized by this relentless solar barrage? The answer is that our planet is protected by an invisible shield, a defense so effective that most of us are completely unaware it even exists, even as it saves us, over and over again. That shield is the Earth's magnetic field. The Earth, like the Sun, generates a magnetic field produced deep within our planet's molten core. This magnetic field extends far out into space, surrounding the entire Earth in a vast, invisible magnetic bubble called the magnetosphere. And this magnetosphere acts as a shield, deflecting the charged particles that stream constantly from the Sun. When the solar wind, the continuous outflow of charged particles from the Sun, reaches the Earth, most of it is deflected around our planet by the magnetosphere, channeled away from the surface, unable to reach us directly. The Earth's magnetic field acts like a force field, parting the stream of solar particles and protecting the life on the surface below. Without this magnetic shield, the constant bombardment of charged particles from the sun would strip away our atmosphere over time and bathe the surface in harmful radiation. The magnetosphere is one of the key reasons life has been able to survive and thrive on Earth. And when a coronal mass ejection arrives, that billion-ton cloud of charged particles, the magnetosphere is our first and most important line of defense. The magnetic field of the Earth absorbs and deflects much of the onslaught, preventing the charged particles from reaching the surface directly. You have actually seen this shield in action, even if you did not realize it. When charged particles from the sun do funnel down along the Earth's magnetic field lines toward the poles, they collide with the gases in our upper atmosphere and cause them to glow, producing the beautiful auroras, the northern and southern lights. Those shimmering curtains of colored light in the polar skies are the visible sign of the Earth's magnetic shield at work, channeling the solar particles toward the poles and lighting up the atmosphere in the process. The aurora is, in a sense, the glow of our planet's defenses absorbing a blow from the sun. But here is the crucial limitation, and the reason a major solar storm is still so dangerous. The magnetosphere is not a perfect, impenetrable barrier. When a powerful coronal mass ejection slams into it, the magnetosphere is compressed, distorted, and violently disturbed. And while it deflects much of the direct particle bombardment, the sheer disturbance of the Earth's magnetic field during a major geomagnetic storm has its own consequences. A rapidly changing magnetic field, it turns out, can induce electrical currents in long conductors on the ground, in power lines, in pipelines, in the very infrastructure of our technological civilization. So even though the magnetosphere protects us from the worst of the direct radiation and particles, the magnetic chaos it undergoes during a major storm can reach down to the surface and wreak havoc on our technology through these induced currents. Our shield protects our bodies, but it cannot fully protect our machines. And it is precisely this vulnerability that makes a major solar flare such a serious threat to the modern world. To understand just how serious, we need to look at what actually gets through and what it can do. We have seen that the Earth's magnetic shield protects us from the worst of a solar storm, but that it cannot fully protect our technology. So let's look closely at exactly what gets through, and how an explosion 93 million miles away can reach down and threaten the machines that modern life depends on. Because the mechanism is both subtle and genuinely alarming. The key danger comes from the way a major geomagnetic storm violently disturbs the Earth's magnetic field. When a coronal mass ejection slams into the magnetosphere, it does not simply bounce off. It compresses and shakes the Earth's magnetic field, causing it to fluctuate rapidly and dramatically. And here is the crucial piece of physics. A changing magnetic field induces electrical currents in any long electrical conductor it passes through. This is a fundamental principle of how electricity and magnetism interact. So when the Earth's magnetic field is violently disturbed during a major storm, it induces electrical currents in the long conductors we have strung across the surface of our planet, our power transmission lines, our pipelines, our cables. These are called geomagnetically induced currents, and they are the primary way a solar storm reaches out and damages our technology. The storm essentially turns our own continent-spanning power grids into giant antennas, picking up the energy of the disturbed magnetic field and channeling it as unwanted electrical current. These induced currents are particularly dangerous to the electrical power grid, and especially to one critical component, the transformer, Power grids rely on large transformers to manage the flow of electricity across vast distances, and these transformers are vulnerable to the extra currents induced by a geomagnetic storm. When a powerful storm induces strong currents in the power grid, those currents can flow into the transformers and cause them to overheat, to be damaged, or even to be destroyed outright. And this is where the real catastrophe lies. Because these large transformers are not simple devices that can be quickly swapped out. They are enormous, expensive, custom-built pieces of equipment, and there is no large stockpile of spares sitting ready. If a major solar storm were to damage or destroy many of them at once, replacing them could take months or even years because they have to be specially manufactured. A widespread loss of transformers could mean widespread, long-lasting blackouts. Beyond the power grid, the disturbance of a major storm reaches our technology in other ways too. The energetic particles and the disturbed atmosphere can damage the delicate electronics aboard satellites, the satellites we rely on for communication, navigation, and weather forecasting. The storm heats the upper atmosphere, causing it to expand and increase the drag on satellites in low orbit, potentially dragging them off course or down toward Earth. The disturbance of the ionosphere disrupts the signals used for GPS and other navigation systems, degrading their accuracy. And the radiation poses a danger to anyone at high altitude or in space. So what gets through a major solar storm is not the direct fury of the flare itself, but a cascade of secondary effects, induced currents, damaged electronics, disrupted signals, all flowing from the violent disturbance of the Earth's magnetic environment. Our shield holds back the worst, but the tremors that pass through it can still bring our technological civilization to its knees. And we do not have to imagine what this looks like, because it has already happened. The clearest warning of all comes from an event over a century and a half ago, when the sun unleashed a storm so powerful it left a mark on history. To truly understand the threat a major solar flare poses, we do not need to rely only on theory and speculation, because the most powerful solar storm in recorded history has already struck the Earth, and it left behind a vivid record of what such an event can do. It happened over a century and a half ago, in the year 1859, and it is known today as the Carrington event. It remains the benchmark, the worst-case scenario, against which all other solar storms are measured. The story begins on the 1st of September, 1859, when a British astronomer named Richard Carrington was observing the Sun, sketching a large and complex group of sunspots on its surface. Suddenly, as he watched, he saw an intense flash of brilliant white light erupt from within the sunspot group, a burst of light so bright and so sudden that he initially thought there might be a problem with his equipment. What Carrington had witnessed, and what another observer independently saw at the same time, was a solar flare, the first one ever recorded by human beings. He was watching, in real time, one of the most powerful eruptions the sun had produced in centuries, a flare blazing across a sunspot region tens of thousands of miles wide. The flash lasted only about 5 minutes before fading, and Carrington could not have fully understood what he was seeing. But he had just observed the visible signature of an enormous release of magnetic energy, and the consequences were about to reach the Earth. Because that flare was accompanied by a massive coronal mass ejection, a colossal cloud of charged particles blasted toward Earth. And this cloud was moving with extraordinary speed. While a typical coronal mass ejection takes 1 to 3 days to reach Earth, this one crossed the entire distance from the Sun to our planet in well under a day, an unusually rapid journey, likely because an earlier eruption had cleared the path before it. Less than a day after Carrington witnessed the flare, the cloud of charged particles slammed into the Earth's magnetic field, triggering the most intense geomagnetic storm ever recorded. The energy involved was staggering, the flare itself estimated to have released energy equivalent to billions of nuclear bombs, and the resulting storm violently disturbed the Earth's magnetic field on a scale never seen before or since in the historical record. What makes the Carrington event so valuable and so frightening is that it gives us a real, documented example of what an extreme solar storm does when it hits the Earth. This was not a near miss or a theoretical scenario. It was a direct, full-force impact from one of the most powerful solar storms imaginable, striking our planet and leaving behind detailed accounts of its effects. And those effects, recorded by the people who lived through it, paint a vivid and unsettling picture of the raw power of the sun unleashed upon the Earth. In 1859, humanity had only just begun to build electrical technology, the telegraph being the most advanced electrical system of the age. And even that primitive technology was thrown into chaos by the storm. To understand what the Carrington event would mean for us today, we first have to see what it did back then, on the night the wires came alive. The effects of the Carrington event, as recorded by the people who witnessed it, read almost like something out of a disaster novel. And remember, this was happening to a world with only the most basic electrical technology. The accounts from that night and the days that followed give us a haunting glimpse of what the sun is capable of when its fury reaches the Earth directly. The most advanced electrical technology of 1859 was the telegraph, the network of wires that carried messages across continents, the closest thing the 19th century had to a global communication system. And when the geomagnetic storm struck, the telegraph networks across Europe and North America descended into chaos. The violently disturbed magnetic field induced powerful electrical currents in the long telegraph wires, exactly the kind of geomagnetically induced currents we discussed, and those currents wreaked havoc on the system. Telegraph operators received severe electric shocks as they worked their equipment. Sparks leaped from the telegraph machines and from the wires. In some places, the surging currents set the telegraph paper on fire. One operator reported receiving a shock so severe it stunned him, with an arc of fire jumping from his equipment. The telegraph system, the technological marvel of its age, was being violently disrupted by an explosion that had occurred on the sun a day earlier. And then came one of the most eerie details of all. Some telegraph operators discovered that they could disconnect their batteries entirely, cutting off their normal power source, and yet continue to send and receive messages using only the electrical current being induced by the storm itself. The geomagnetic storm was supplying so much electrical energy to the telegraph lines that the operators no longer needed their own power. They were running their telegraphs on the raw current induced by the disturbed magnetic field of the Earth, on the energy of the solar storm flowing through their wires. Imagine that. The sun's eruption was, in effect, powering the telegraph network directly, an unsettling demonstration of just how much electrical energy the storm was pumping into the infrastructure of the time. Beyond the telegraph chaos, the skies themselves put on a display unlike anything in living memory. The auroras, normally confined to the regions near the poles, blazed across the sky at latitudes where they are almost never seen. People as far south as the Caribbean witnessed brilliant auroras overhead. The auroras were so bright in some places that people could read a newspaper by their light in the middle of the night. In some locations, the glow was so intense that birds began to sing, and people rose to begin their day, believing that dawn had broken. Others, seeing the blood-red glow on the horizon, feared that distant towns or forests were ablaze. It was a planet-wide spectacle, beautiful and unsettling in equal measure, the visible sign of an enormous solar storm enveloping the Earth. The Carrington event was, by every account, an overwhelming demonstration of the sun's power. And here is the truly sobering thought. In 1859, the chaos was largely limited to telegraph wires and beautiful skies, because there was little electrical technology to disrupt. Today, our entire civilization runs on the very kind of technology that stormed through into chaos. To understand what that means, we can look at more recent events, when smaller storms gave us a taste of the danger. The Carrington event happened in a world with almost no electrical technology, so its true potential for destruction was never fully realized. But in more recent times, even smaller solar storms have struck a world increasingly dependent on technology, and they have given us very real, very concrete demonstrations of the danger. These modern events are warnings, previews of what a larger storm could do to our civilization. The most striking example occurred a few decades ago, when a geomagnetic storm struck the Earth and caused a major power blackout across a large region. The storm induced powerful currents in the electrical power grid, and those currents overwhelmed the system. In a matter of seconds, a major regional power grid collapsed entirely, plunging millions of people into darkness. The blackout struck with astonishing speed, the grid failing in well under 2 minutes, and it left millions without electricity for many hours. This was not a minor flicker. It was the complete collapse of a major power grid, caused directly by a solar storm, affecting millions of people. And it demonstrated in the clearest possible terms that the threat we have been discussing is real. A solar storm had reached down from space and switched off the power for an entire region, exactly as the physics predicted it could. The induced currents, the vulnerable transformers, the cascading failure, all of it played out in reality. More recently, the sun has continued to remind us of its power. During the recent surge of solar activity, the Earth was struck by the strongest geomagnetic storm in over 2 decades. A series of powerful flares and coronal mass ejections, erupting from a single enormous active region on the Sun, sent multiple clouds of charged particles racing toward Earth, where they combined to produce a major geomagnetic storm. This storm lit up the skies with auroras seen at remarkably low latitudes, far from the poles, in one of the most widespread auroral displays in centuries. People who had never seen the northern lights in their lives suddenly found the sky glowing above them. The storm caused disruptions to certain technologies, including interference with the precise navigation systems used in some industries, but it stopped short of catastrophe. It was, in many ways, a near miss, a powerful storm that gave us a vivid display and some disruption, but spared us the worst. Yet it served as a stark reminder that the sun is fully capable of striking the Earth with major storms in our own time. These modern events carry a crucial lesson. Each of them was caused by a solar storm considerably weaker than the Carrington event. And yet, even these lesser storms were able to collapse a major power grid and disrupt technology across the globe. If storms weaker than the Carrington event can cause this kind of damage to our modern, technology-dependent world, then the prospect of a true Carrington-class storm striking today becomes genuinely alarming. We have built a civilization that runs entirely on the kind of technology that solar storms disrupt, and we have already seen smaller storms cause real harm. The modern reminders tell us unmistakably that this is not a hypothetical threat. It is a real one, and it is only a matter of time before a larger storm arrives. And the most frightening part is that a true Carrington-class storm came within a hair's breadth of striking us just over a decade ago, and almost no one realized how close we came. Of all the solar events of recent times, there is one that should genuinely keep us up at night. It was not a storm that struck the Earth, but one that very nearly did. Just over a decade ago, the Sun unleashed an eruption every bit as powerful as the Carrington event, a true monster, a full-strength Carrington-class storm, and it crossed the Earth's orbit, racing through the exact region of space our planet occupies. The only reason it did not strike us, the only reason we are not still recovering from it today, is timing. It missed the Earth by a margin of just 9 days. Here is what happened. The Sun produced an enormous eruption, launching one of the fastest and most powerful coronal mass ejections ever observed, a cloud of charged particles comparable in scale to the one that caused the Carrington event. This colossal storm blasted out from the Sun and raced through space, crossing the orbital path of the Earth. But the Earth, in its journey around the Sun, simply was not at that point in its orbit at the moment the storm passed through. Our planet had been at that very location in space only days earlier. If the eruption had occurred just over a week sooner, the Earth would have been directly in its path, and the storm would have struck us with full force. As it happened, the cloud of charged particles swept harmlessly through the region of space where the Earth would have been, missing our planet by that narrow margin of timing. We were, quite simply, extraordinarily lucky. What makes this event so chilling is that scientists were able to study it in detail, because although it missed the Earth, it was observed by a spacecraft positioned to detect it. And their analysis confirmed that this storm was indeed a true Carrington-class event, fully capable of causing the kind of catastrophic damage we have been discussing. Scientists who studied it concluded in stark terms that if it had struck the Earth, we would still be dealing with the consequences, picking up the pieces, years later. The damage to our power grids, our satellites, our communications, and our infrastructure could have been staggering, potentially running into trillions of dollars and taking many years to fully repair. This was not a minor storm. It was the real thing, a genuine Carrington-class monster, and it passed through our orbit just days after we had moved out of the way. Think about what this means. We tend to assume that a catastrophic solar storm is a distant, unlikely possibility, something that might happen far in the future, if at all. But the reality is that a full-strength Carrington-class storm came within 9 days of striking our modern, technology-dependent civilization, and almost no one outside the scientific community even noticed. It was a genuine near miss, a brush with potential catastrophe that we escaped purely by the luck of orbital timing. The Sun fired a shot powerful enough to devastate our civilization, and it missed us by a margin that, on cosmic timescales, is almost nothing. This event should fundamentally change how we think about the threat of solar storms. It is not a question of whether a Carrington-class storm will come, but when. And we have already seen in our own time just how close one can come. So let's confront, directly, what would actually happen if such a storm struck the Earth today. We have seen what the Carrington event did to the world of 1859 with its primitive telegraph technology. We have seen smaller modern storms collapse power grids and disrupt technology, and we have seen a true Carrington-class storm miss us by just 9 days. So now let's ask the question that really matters. What would happen if a storm as powerful as the Carrington event struck the Earth today, in our world of total technological dependence? The answer is genuinely frightening, and it explains why scientists take this threat so seriously. The single greatest concern is the electrical power grid. Our entire civilization runs on electricity, and that electricity is delivered through vast power grids spanning entire continents. Grids built from exactly the kind of long conductors and vulnerable transformers that solar storms attack. If a Carrington-class storm struck today, it would induce enormous electrical currents in these power grids, currents far beyond what smaller storms have already shown can collapse a regional grid. The result could be the failure of power grids across entire continents, plunging vast regions into darkness. And the most alarming part is the potential damage to the large transformers that the grid depends on. If the storm were to damage or destroy large numbers of these transformers simultaneously, the blackout would not be a matter of hours, as in past events. Because these transformers are enormous, custom-built, and not stockpiled in large numbers, replacing many of them at once could take months or even years. We could be looking at widespread power outages lasting not hours, but potentially many months, across huge areas. Now try to imagine what a blackout of that scale and duration would actually mean for modern life. Nearly everything we depend on requires electricity. Without power, the systems that pump and purify our water would fail. The systems that keep food refrigerated and that move it through the supply chain would stop. Hospitals would be forced to rely on backup generators, which themselves require fuel that must be pumped and delivered using electricity. Communication networks, the internet, mobile phone systems, all of it depends on electrical power and would be severely disrupted. Financial systems, which now exist largely as electronic records, could be thrown into chaos. Modern society is built on the assumption of constant, reliable electricity, and a months-long blackout across entire continents would unravel that assumption catastrophically. The consequences would cascade through every aspect of life, affecting food, water, healthcare, communication, finance, and public order. It is not an exaggeration to say that a sufficiently powerful and widespread solar storm could pose an existential challenge to modern civilization as we know it. And the economic cost would be staggering. Studies that have attempted to estimate the financial impact of a major Carrington-class storm striking today have arrived at figures in the trillions of dollars, with recovery taking many years. It would be one of the most expensive natural disasters in human history, potentially the most expensive of all. And this is not a far-fetched scenario dreamed up by alarmists. It is the sober assessment of scientists who study these events, based on the documented power of past storms and the known vulnerabilities of our technology. The Carrington event was real. The 2012 near miss was real. The collapse of power grids by smaller storms was real. A Carrington-class storm striking our modern world is not a question of if, but when, and the consequences could be catastrophic. But the threat to the power grid, severe as it is only one part of the picture, because a major solar storm would also reach into the skies, threatening the vast web of technology we have come to depend on without even thinking about it. The power grid is the most obvious target of a major solar storm, but it is far from the only one. Our modern civilization is held together by an invisible web of technology, much of it in the skies above us, and almost all of it is vulnerable to the fury of the sun. To understand the full scope of the threat, we have to look at just how deeply we now depend on systems that a solar storm could cripple. Consider the satellites orbiting our planet. There are now thousands of them, and they form the backbone of modern life in ways most people never think about. Satellites provide our global positioning and navigation, our long-distance communications, our weather forecasting, our television and internet signals, and far more. And these satellites are extraordinarily vulnerable to a major solar storm. The flood of energetic particles from a major eruption can damage their delicate electronics, degrade the solar panels that power them, and build up dangerous electrical charges that can short-circuit their systems. On top of that, a major storm heats and expands the Earth's upper atmosphere, increasing the drag on satellites in low orbit, which can pull them off course or drag them down toward the Earth. We have already seen smaller storms destroy satellites through this increased drag. A Carrington-class storm could damage or destroy large numbers of satellites at once, knocking out the navigation, communication, and observation systems that modern society relies on in a single blow. Then there is the global positioning system and the other navigation networks that we now depend on for far more than just finding our way. Modern navigation signals are used not only for directions, but for the precise timing that synchronizes financial transactions, power grids, communication networks, and countless other systems. And these signals travel through the upper atmosphere, the ionosphere, which a major solar storm violently disturbs. During a powerful storm, navigation signals can be degraded or knocked out entirely, throwing off everything that depends on them. Aircraft, ships, emergency services, agriculture, finance, and a vast range of industries rely on these signals, and a major storm could disrupt them all at once. The same disturbance of the upper atmosphere also blacks out high-frequency radio communications across the sunlit side of the Earth, the very communications that aircraft on long polar routes depend on, forcing them to reroute and disrupting air travel. What makes all of this so dangerous is how interconnected and interdependent these systems have become. Our power grids, satellites, navigation, communications, finance, and supply chains are all woven together into a single, complex web, each part depending on the others. A major solar storm would not strike just one of these systems. It would strike many of them simultaneously, and because they are so interdependent, the failures would cascade and compound one another. The loss of power would disrupt communications. The loss of satellites would disrupt navigation and finance. The loss of navigation timing would disrupt the power grid and the financial system. Each failure would amplify the others, potentially bringing down the entire web of technology that modern civilization depends on. We have built an extraordinarily powerful, but also extraordinarily fragile technological world, and we have built it directly beneath a star capable of explosions that could tear that web apart. And the danger is not only to our machines. It is also to the human beings who venture beyond the protection of the Earth. There is a cruel irony at the heart of this entire story, and it is worth confronting directly, because it transforms the threat of a solar flare from a stable, unchanging danger into one that is growing more severe with every passing year. The irony is this: the more advanced and powerful our civilization becomes, the more vulnerable we are to the sun. Our greatest strength, our technology, is also our greatest weakness when our star unleashes its fury. Think back to the Carrington event of 1859. It struck a world that had barely begun to use electricity. The most advanced electrical system of the age was the telegraph. And while the storm threw the telegraph network into chaos, the damage was ultimately limited, because society simply did not depend on electrical technology for its survival. People still lit their homes with candles and oil lamps, traveled by horse and steam, stored food without refrigeration, and lived lives that electricity played almost no part in. A Carrington-class storm was a spectacle and a disruption, but not a catastrophe, because there was so little electrical technology for it to destroy. The world of 1859 could absorb a direct hit from the most powerful solar storm in history and carry on largely unharmed. That same storm today would be a different matter entirely. Now consider how the stakes have risen over time. By the late 20th century, when a far weaker storm collapsed a major power grid and blacked out millions of people, Society had become deeply dependent on electricity, and so a storm that would have been trivial in 1859 caused real and significant harm. The danger had grown, not because the sun had changed, but because we had. We had built a civilization that ran on the very technology solar storms attack, and in the decades since, our dependence has only deepened dramatically. Today, virtually every aspect of modern life runs on electricity, on satellites, on global navigation, on the internet, on interconnected digital systems. We have electrified our transport, digitized our money, networked our communications, and come to rely on a constellation of satellites and a web of power grids for nearly everything we do. We have, in effect, built our entire civilization on exactly the kind of technology that a major solar storm could cripple. And the trend is accelerating. With each passing year, we add more satellites to orbit, electrify more of our world, digitize more of our lives, and deepen our reliance on the vulnerable systems the sun can disrupt. This means that the same solar storm would do more damage today than it would have a decade ago, and more damage a decade from now than it would today. The threat is not static. It is growing, in lockstep with our own technological advancement. We are, paradoxically, making ourselves more vulnerable to the sun the more powerful and sophisticated we become. The world has never been more capable, and it has never been more exposed to the fury of our star. We have built a magnificent technological civilization, optimized for a calm and cooperative sun, on a star that is not always calm, and that periodically unleashes explosions powerful enough to tear that civilization's foundations apart. The longer we go without a major storm, the more we build, and the more we have to lose when one finally arrives. That is the uncomfortable truth at the center of the solar flare threat. The sun has not grown more dangerous. We have grown more fragile. And nowhere is that fragility more sharply felt than for the human beings who leave the safety of the Earth entirely. So far, we have focused on the threat a solar flare poses to our technology. But there is another danger, one that is far more immediate and far more lethal to any human being who happens to be in the wrong place at the wrong time. Because the Earth's magnetic field and atmosphere protect us on the surface, but they do not protect anyone who ventures beyond them. For astronauts in space, a major solar flare is not just a threat to their equipment. It is a potentially deadly threat to their lives. Here on the surface of the Earth, we are shielded from the energetic particles of a solar storm by both our planet's magnetic field and our thick atmosphere. But an astronaut in space, especially one beyond the protective bubble of the magnetosphere, has no such shield. When a major solar flare erupts and floods space with high-energy particles, an astronaut caught in that radiation could receive a massive dose, enough to cause severe radiation sickness, and in the most extreme cases, enough to be lethal. Eruption can be deadly to an unprotected human being. An astronaut on the surface of the moon, for example, which has no magnetic field or atmosphere to provide protection, would be terrifyingly exposed during a major solar storm. A sufficiently powerful flare could deliver a fatal dose of radiation to anyone caught on the lunar surface without adequate shelter. This is one of the gravest dangers facing human space exploration. And this is not merely a theoretical concern. During the era of the first missions to the moon, humanity got extraordinarily lucky. One of the most powerful solar storms of the 20th century erupted during the period when astronauts were traveling to and from the moon, in the gap between two of the crewed lunar missions. Had that storm erupted while astronauts were actually on the surface of the moon or traveling through space, they could have received a dangerous, possibly lethal, dose of radiation. The timing, once again, spared us a tragedy, but it was a stark warning of the danger. The sun had unleashed a storm powerful enough to potentially kill astronauts on the moon, and it happened to occur when no one was there to be harmed. It was a close call that highlighted just how vulnerable astronauts are to the sun's fury. This danger has profound implications as humanity looks to return to the moon and to journey onward to Mars. Future astronauts venturing beyond the protection of the Earth's magnetic field will be exposed to the threat of solar radiation, and a major solar flare erupting during a mission could be catastrophic. This is why protecting astronauts from solar radiation is one of the central challenges of deep space exploration. Future missions will need shelters where astronauts can take refuge during a solar storm, and reliable systems to warn them when a flare has erupted, so they can seek protection in time. The dream of exploring the moon and Mars must contend with the reality that the sun can, at any moment, flood space with deadly radiation. The same explosions that threaten our power grids on Earth threaten the very lives of those who would venture out to explore the cosmos. And as frightening as everything we have discussed already is, there is a deeper question lurking behind it all. Could the sun produce a flare even more powerful than the Carrington event? Could the worst be far worse than anything in our records? Throughout this exploration, we have treated the Carrington event as the worst-case scenario, the most powerful solar storm in recorded history, the benchmark of solar fury. But here is a deeply unsettling question. Is the Carrington event truly the worst the sun can do? Or is it possible that our star is capable of producing flares even more powerful, eruptions so extreme that they would make the Carrington event look modest by comparison? The evidence suggests that the answer may be yes, and that is a genuinely sobering thought. Our direct records of solar storms only stretch back a relatively short time, to the era when we first began observing the sun and measuring its activity in detail. The Carrington event is the most powerful storm within that limited window of direct observation. But the sun has been erupting for billions of years, and a window of a century and a half is a tiny sliver of that history. To learn about solar storms before our records began, scientists have turned to other sources of evidence, clues preserved in the natural world. When the sun unleashes an extremely powerful storm, the flood of particles striking the Earth leaves subtle traces, altering the amounts of certain rare forms of atoms that get locked into tree rings and into the layers of ancient ice. By examining these natural records, scientists can detect the signatures of major solar events that occurred long before anyone was measuring the sun. And what these natural records reveal is alarming. They show evidence of solar storms in the past that were far more powerful than the Carrington event, eruptions so extreme that they dwarf anything in our direct historical record. Several times in the past few thousand years, the Earth appears to have been struck by solar events of staggering intensity, events that would be catastrophic beyond imagining if they struck our modern civilization. These ancient superstorms suggest that the sun is capable of eruptions significantly more powerful than the Carrington event, perhaps many times more powerful. The Carrington event, in other words, may not be the ceiling of the sun's power. It may merely be the most powerful storm that happened to occur during our brief window of observation, with far greater storms lurking in the sun's deeper history and potentially its future. This possibility is reinforced by observations of other stars similar to our sun. When astronomers study distant stars like the sun, they sometimes catch them producing enormous flares, eruptions vastly more powerful than anything our sun has produced in recorded history. These superflares, observed on other sun-like stars, release energy on a scale that would be devastating beyond comprehension if produced by our own star. While there is debate about exactly how often our particular that similar stars do produce them, suggests that our sun may be capable of the same. The implication is profound and frightening. The worst solar storm we have on record may be far from the worst the sun can actually do. Somewhere in the sun's capabilities may lie eruptions so powerful that they would pose a truly existential threat to our technological civilization, and perhaps even more. We have been treating the Carrington event as the nightmare scenario, but the real nightmare may be considerably worse. So the question becomes urgent. If the sun is capable of such fury, what can we possibly do to protect ourselves? Given everything we have learned, the threat of a major solar flare can feel overwhelming, even hopeless. The sun is capable of explosions equivalent to billions of nuclear bombs, and we cannot prevent them. We cannot stop the sun from erupting. We cannot shield the entire Earth from a major storm. So is there anything we can actually do? The answer, encouragingly, is yes. While we cannot stop a solar flare, we can watch for it, prepare for it, and take action to limit the damage. And humanity has been quietly found. We now have a fleet of spacecraft and ground-based observatories dedicated to watching the sun around the clock, monitoring its surface for the telltale signs of building magnetic stress, and detecting flares and eruptions the moment they occur. Specialized satellites constantly measure the sun's output, including the X-rays that signal a flare, allowing scientists to detect an eruption almost instantly. Other spacecraft watch for coronal mass ejections, those billion-ton clouds of charged particles, and track their progress as they race through space. Because a coronal mass ejection takes 1 to 3 days to reach the Earth, this monitoring gives us something precious that the 8-minute radiation does not. Warning time. When scientists detect a major eruption heading toward Earth, they can forecast its arrival and issue alerts, giving us hours or even a day or more to prepare for the storm's impact. We have, in effect, built an early warning system for solar storms, a network of watchful eyes trained on our star. And that warning time, even if it is only hours, can make an enormous difference. With advance notice that a major storm is coming, the operators of power grids can take protective action, adjusting the flow of electricity, reducing loads, and disconnecting vulnerable equipment to limit the damage from induced currents. Satellite operators can put their spacecraft into protective modes, shutting down sensitive systems to help them ride out the storm. Airlines can reroute flights away from the polar regions where the radiation and communication disruptions are worst. Astronauts can take shelter in the most shielded parts of their spacecraft, and other critical systems can be safeguarded as much as possible. None of this can fully eliminate the threat, but it can significantly reduce the harm, potentially preventing the worst outcomes, like the permanent destruction of critical transformers. Forewarned is, to a meaningful degree, forearmed. But here is the crucial caveat. Our defenses are only as good as our willingness to take the threat seriously and to invest in preparation. The warning systems must be maintained and improved. Power grids and other critical infrastructure must be hardened against the effects of solar storms, made more resilient so they can survive a major event. Spare transformers and contingency plans. If the worst happens, recovery can be swift. And it is only a matter of time before a major storm arrives, but it is not a danger we are helpless against. With vigilance, preparation, and investment, we can dramatically reduce the harm a major solar flare would cause. The question is whether we will take the threat seriously enough to act before, rather than after, the storm arrives. Because the sun will not wait for us to be ready. It will erupt on its own schedule, indifferent to our preparations, and we would be wise to be ready when it does. So the next time you step outside on a bright, clear day, and you feel the warmth of the sun on your face, take a moment to consider the true nature of the star you are standing beneath. Because that rises each morning of the most powerful explosions in the entire solar system, and it produces them far more often than you might ever imagine. Somewhere on the surface of the sun, perhaps at this very moment, the magnetic fields are twisting and winding, storing up energy, straining toward their breaking point. And at some moment, without warning, they will snap, releasing in a single flash the energy of billions of nuclear bombs, heating matter hotter than the core of the sun, blazing across a region of the surface large enough to swallow our entire world many times over. It will be the most violent event in the solar system, and it will happen in complete silence, invisible to anyone looking up. The flash you would never notice will erupt, pour its radiation across the gulf of space, and in 8 minutes, some of that energy will brush past the Earth. Most of the time, our planet's invisible shield will turn it aside, and we will carry on unaware. But the sun is always capable of more. We have built a remarkable civilization, a world of electricity and satellites and global communication, a web of technology that connects every corner of the planet. It is a triumph of human ingenuity. And yet, we have built it directly beneath a star that can, at any moment, unleash an explosion capable of tearing that web apart. We have already had our warnings. The night the telegraph wires caught fire in 1859, the day a storm switched off the power for millions in a matter of seconds. The Carrington-class monster that crossed our orbit and missed us by just 9 days. The sun has shown us again and again what it is capable of, and the ancient records hint that it may be capable of far worse, of eruptions so powerful they would dwarf anything in our experience. We live, whether we acknowledge it or not, at the mercy of our star. But there is no need for despair, only for respect and for vigilance. The sun is not our enemy. It is the source of all the energy that has ever powered life on Earth, the reason we exist at all. Its flares are not acts of malice, but simply the natural behavior of a churning, magnetic star, the same processes that make it shine. Our task is not to fear the sun, but to understand it, to watch it, and to prepare for the moments when its power turns toward us. We have built the watchful eyes to see a storm coming. We have the knowledge to harden our defenses and limit the damage. What remains is the wisdom to take the threat seriously, to act before the storm arrives rather than after. The sun will continue to erupt, as it has for billions of years, indifferent to the small, clever creatures living on the third planet. Whether those creatures are ready is up to them. So look up, sometimes, at that bright and gentle sun, and remember what it truly is. Not just a source of warmth and light, but a vast, churning, magnetic engine capable of explosions beyond all human comprehension. It has given us everything, and it holds in its twisting magnetic fields a power that could one day test our civilization as nothing ever has. The flash is silent, the danger is real, and the most powerful explosion in the solar system is never more than a moment away on the surface of the star we so easily take for granted. Respect it, watch it, and never forget how small we are and how much we owe to the terrifying and magnificent star at the center of our world.